This is a presentation that was given to the Montgomery Amateur Radio Club in Rockville, Maryland, as the introductory part of a J-pole design and construction project. The goals of this project were twofold. One was to walk away with a working J-pole antenna that could be used with a handheld VHF-UHF transceiver. But two was also to walk away with a better understanding of transmission lines, the Smith chart, and vector network analyzers, which will be used in the design and testing of these antennas. So what exactly is a transmission line? A transmission line is a two-port network which connects a source, for example, signal generator or transmitter, at the sending end to a load, for example, a dummy load or antenna, at the receiving end. At high frequencies, where the wavelength is much smaller than circuit dimensions, this can result in different phases at different locations along the transmission line, and therefore requires a somewhat different analysis approach. This problem was first observed in the mid-1800s when telegraph transmissions over transatlantic distances were first attempted. The variations in amplitude and phase along the line created substantial signal distortion and attenuation, which ultimately limited the speed at which data could be sent. For example, in 1858, President James Buchanan received the very first public message over transatlantic cable from Queen Victoria to celebrate, quote, a link between nations. The transmission was 98 words long, but took a whopping 16 and a half hours to transmit. Today, there are many types of transmission lines, ranging from coaxial structures, or coax, to parallel lines, such as twin lead or ladder line, to printed circuit board microstrip and strip line, to waveguides. In the first three examples, transmission occurs along a metallic conductor which is supported by dielectric material, whereas with waveguide, transmission occurs within a hollow metal tube in which the metal walls provide distributed inductance and the empty space between the walls provides distributed capacitance. Here is a cross-section of a piece of LMR 400 low-loss coaxial cable, commonly used at VHF and UHF frequencies. As you can see, there is a center, in this case solid conductor, surrounded by a low-loss dielectric material, dielectric polyethylene foam, which is in turn surrounded by foil and tin copper braid shields. A UV-resistant outer jacket is used to protect the cable from outside elements. As mentioned earlier, the longer the cable, the more signal distortion one observes. In 1855, about 3 years before that first transcontinental cable was completed, Professor William Thomson, later known as Lord Kelvin, predicted the poor performance of the 1858 transatlantic submarine cable by formulating a diffusion model for a transmission line consisting of distributed resistance and capacitive elements. About 26 years later, in 1884, the concept of inductance was finally quantified by Oliver Heaviside, and this led him to the more accurate model for a transmission line that we see here. If we take an infinitesimally small piece of coaxial line having length delta Z, Heaviside modeled it as a set of series elements consisting of resistance R prime delta Z, where R prime is the resistance per unit length, and inductance L prime delta Z, where L prime is the inductance per unit length. In addition, he added a set of parallel elements consisting of a capacitance C prime delta Z and conductance G prime delta Z, where again C prime and G prime are parameters per unit length. The resistance R prime represents the ohmic loss in the center conductor and the outer braid. Parameter L prime represents the inductance that the center conductor and outer braid exhibited. The parameter C prime represented the capacitance seen between the center conductor and the outer braid, and G prime represented the ohmic losses in the dielectric material, which is expressed in this case as conductance, that is reciprocal of resistance. Heaviside took these small infinitesimal models and then strung them together to form the cable and looked at what happened when delta Z goes to zero. So as delta Z goes to zero, we get a better and better approximation to the characteristics of the cable. This approximation technique is probably familiar to those who have taken a course or two in calculus. The analysis of this circuit equivalent of a transmission line is actually straightforward. And this follows from applications of Kirchhoff's voltage and current laws. Kirchhoff's voltage law states that the sum of the voltage differences around any closed loop in a circuit must be zero. And this is the loop we're talking about. So therefore, the voltage at the left-hand side of the loop, V of ZT, must be the sum of the voltages in the other part of the loop. And in this case, we have a voltage that comes across the resistance, R delta Z, and the voltage across that resistor is simply its resistance times the current flowing through it, which is I of ZT. The voltage across the inductance is given by the inductance times the rate of change of current, L di dt. In this case, the inductance is L delta Z, and the rate of change is delta I of ZT, the current flowing through it, dt. And finally, the voltage that is across the parallel element, G and C, is given simply by V of Z plus delta Z, T. Note that V of ZT is on the left-hand side of this infinitesimally small piece of transmission line of length delta Z. And delta Z units of distance later, we end up with V of Z plus delta Z at time t. Kirchhoff's current law, on the other hand, states that the total current flowing into a node or junction in a circuit must be equal to the total current flowing out. Again, a fundamental conservation of energy law. So let's look at node N in this case. In node N, we have current I of ZT flowing into it, and flowing out of that node, we have several currents. We have the currents that are flowing through the conductance G and the capacitance C. Well, the conductance current is G delta Z, which is the conductance, times the voltage across that conductor, which is V of Z plus delta ZT. Similarly, the current flowing through the capacitor is simply the capacitance times the rate of change of voltage across the capacitor, and that just follows from elementary circuit rules. In this case, the capacitance is C delta Z, and again, the voltage across the capacitor is the same as it is across the conductance, which is V of Z plus delta Z T. And finally, we have one last term, and that's the term of current that flows out to the next part of the circuit, and that is simply the current I of Z plus delta Z T. And the sum of those must be equal to zero. So now let's consider the case when we let delta Z, in other words, this small differential in spatial coordinates, go to zero. If we do that and look at these two equations, we end up with a pair of coupled differential equations, which are known as the telegrapher's equations. And this comes from Heaviside's 1885 paper. The reason they're called telegrapher's equations was that at that time, in 1885, the main means of communication was across cables, and in particularly via telegraphy or Morse code. With Heaviside's telegrapher equations, together with the knowledge of our source and load impedances, we could theoretically determine everything we need to know about the transmission of energy down a transmission line. However, in the case of interest here, we really only care about the steady state solution to these equations, as we're not interested in transient effects that might occur, for example, with the transmission of a pulse along the line, or in power up, or in time-domain reflectometry applications, for example. It can be shown that a natural consequence of Heaviside's distributed model for a transmission line is the existence of both forward and backward traveling waves. The voltage V of Z at any point along the transmission line, as well as the current I of Z along any point on the line, is given by these two relationships. V of Z is V0 plus e to the minus gamma Z, which is the forward traveling wave, plus a term which is a backward traveling wave, V0 minus e to the plus gamma Z. Note that the negative sign disappears here because Z is moving in the opposite direction. In both cases, we end up with a decaying exponential. Same thing true for the current. The parameter gamma in these equations is given by a real term alpha plus an imaginary term j beta. Alpha is what is known as the attenuation constant, and j beta is known as the phase constant, or beta itself is known as the phase constant. From the telegrapher's equations, we also know that gamma is equal to the square root of the product of the R plus j omega L and G plus j omega C. The interesting point, though, is that the ratio of the voltages along the line, V0 plus and I0 plus, or V0 minus and I0 minus, in other words, the ratio of the impedance for the forward traveling wave or the backward traveling wave is given by the same relationship, which is a square root of R plus j omega L over G plus j omega C. And this will define to be Z0, or the characteristic impedance of the transmission line. And we'll see why this is called the characteristic impedance in a few slides from here. So again, Z0 is known as the characteristic impedance of the transmission line. It's a function of those four parameters, R, L, G, C. And gamma, which is a sum of a attenuation constant and a phase constant, is called the complex propagation constant of the transmission line. And that's also given as a function of those four parameters. These are perhaps the most important parameters of the transmission line and do not depend upon the transmission line's length, but on the distributed parameters R, L, G, C and the frequency of operation omega. Let's specialize that a little bit further for a low loss line or a lossless transmission line, or alternatively when the line is very, very short. Then R is approximately 0. In other words, there's very little ohmic loss along the line. And G, which is the conductance across the dielectric material, is also very, very small, or 0. G being 0, remember, that's a reciprocal of resistance, so that implies that the resistance across the dielectric is extremely large. So if we let R go to 0 and G go to 0, then the characteristic impedance from the equation we saw in the previous slide goes to square root of L over C, which is a real number. In other words, the characteristic impedance of a low loss or lossless transmission line is purely real. In general, that's not the case. You buy coax at 50 ohms, you are approximating a impedance of 50 ohms, or a characteristic impedance of 50 ohms, but it's not quite there. We'll see that in some view graphs further on. The attenuation constant now you can show is equal to 0. In other words, there's no attenuation along the line, but the phase changes, obviously, as a function of the position. So with a little mathematics, we can show that if we terminate a transmission line in a impedance ZL, a load impedance ZL, then the impedance looking into the line at this point is going to be a function of ZL, the characteristic impedance, the length of the line, and the wavelength at which we operate. So in the case of the lossless transmission line, the impedance looking into the lossless line is given by the characteristic impedance Z0 times the ratio of these two terms, which are a function of ZL, the characteristic impedance, the length of the line, and the wavelength lambda. Well, we're finally getting to an interesting relationship for transmission lines that we'll be using in our J-pole design. Let's take a look again at that lossless case where we know that the impedance looking into the line at any given point is given by the relationship in the upper box. Let's look at 4 specific cases. One, when the impedance at the end of the line, in other words, the load impedance, is equal to the characteristic impedance Z0. If that's the case, you can see that this right-hand term turns to 1. In other words, Z0 plus JZ0, Z0 plus JZ0, it all cancels out. So the impedance at any given point on the line, no matter what D is, and no matter what the wavelength is, the characteristic impedance is equal to the source impedance. In other words, looking into the line, we can see Z0 no matter where we are. That's called a matched transmission line for obvious reasons. Now let's look at the case when we have an open circuit, when ZL goes to infinity. So we open up the end of the line and we calculate the impedance looking into that line. If you do the calculations, you'll see that if the length of the line is less than a quarter wavelength, then the impedance looking into the line for an open circuit looks like a capacitor. It's minus J times some number here, which is a function of D and lambda and Z0. So for small sections of line which are less than a quarter wavelength, an open line looks like a capacitive reactance. Similarly, if I short the line and set ZL equals 0, then looking into that piece of transmission line looks like an inductor as long as D is less than lambda over 4. Note that the tangent function actually repeats. So this occurs not only for lambda over 4 or less, but also for 2 pi beyond that, and 4 pi, 6 pi, 8 pi, etc. So it keeps repeating itself. These two relationships, 2 and 3, are actually very useful when you're looking at microstrip circuits and you want to be able to make a capacitor or inductor at a specific microwave frequency, because the dimensions are very, very small. So you can make a capacitor very, very accurately by essentially putting a open circuit piece of or stub of transmission line on your circuit board, similarly for an inductor. Now, the special case that we're interested in here is when the length of the line is precisely a quarter wavelength. If that's the case, then everything cancels here and you get ZS, which is the source impedance or the impedance looking into the line, is the square of the characteristic impedance divided by the load impedance. It's kind of an interesting equation. If I divide both sides by Z0, then I end up with the normalized impedance, the impedance looking into the line, which is ZS divided by the characteristic impedance, is equal to the reciprocal of normalized impedance on the other end. So the Z load over Z0 is the normalized impedance at the load. The reciprocal of that is equal to the impedance looking in. So in other words, the quarter wave line acts as an impedance transformer. If I have a high load impedance, ZL is very, very high, this ratio becomes very, very small, and so the source impedance looks like a short circuit. If I have a very low impedance at the end of the line, then this becomes a very high impedance on the other end. So it's a way of taking very high impedances, moving them to very low, and vice versa. And this is a characteristic that we're going to be using for matching our J-pole design. There are a couple other equations that are useful to look at. One is when we have a impedance ZL at the end of the line and look at a quarter wavelength. For a quarter wave line terminated in impedance ZL, I can actually determine what the characteristic impedance is by measuring the impedance looking into that line. So in this case, Z0, which is the characteristic impedance, is equal to the square root of the impedance looking into the transmission line times the load impedance. So for example, if I put 1,000 ohms at the end of my piece of coax and measure the impedance looking into the piece of coax, if I take the square root of that product, I'll end up with a close approximation to what the characteristic impedance is. And finally, if I short circuit the end of the line and open circuit the end of the line and measure the impedances looking into the line in both cases, take the square root of that, I also end up with Z0. We'll end up using both of these relationships a little bit later to calculate what the characteristic impedance and also what's called a velocity factor is for a piece of coax. As was mentioned earlier, the steady-state solutions to Heaviside telegrapher equations consisted of both a forward traveling wave, V0 plus e to the minus gamma z, and a backward traveling wave, V0 minus e to the plus gamma z. Note that the gamma minus z exponent shows that the wave amplitude dies down with distance as a function of losses in the line. And similarly for the backward traveling wave, notice that there's a negative sign missing here because the traveling wave is moving toward the source and it's decaying at a rate e to the plus gamma z, where z is negative now. The ratio of the two wave amplitudes, that is V0 minus to V0 plus, is referred to as the reflection coefficient, as it represents the ratio of reflected to incident voltages. From the transmission line equations, it can be shown that this reflection coefficient, we'll call it gamma, is given by ZL minus Z0 divided by ZL plus Z0. Remember that ZL is the load impedance. Z0 is the characteristic impedance of the transmission line. We also know it as the parameter S11, which is a so-called scattering coefficient or scattering parameter. Philip Smith, working at Bell Laboratories around 1939, along with two of his co-workers, came up with an ingenious way of graphically solving the transmission line equations for an arbitrary load impedance and transmission line parameters. Parenthetically, Smith was actually beaten to the punch 2 years earlier by a Japanese researcher, Mizuhashi Tosaku, but they both actually developed the concept independently. MIT's radiation laboratory was a very big user of Smith's graphical tool during World War II and referred to it in its publications as the Smith chart, a name which has stuck, and nearly everyone universally today refers to this as the Smith chart. What Smith did was to graphically map the two-dimensional Cartesian complex plane, x plus jy, into the unit circle using the transformation gamma is equal to ZL minus Z0 divided by ZL plus Z0. If the load impedance ZL has a real component which is greater than or equal to 0, then the value for gamma would lie somewhere within this unit circle. If the load impedance, on the other hand, had a negative real component, negative resistance, as for example an oscillator might have, then gamma would lie somewhere outside the unit circle. So the Smith chart was usable not only for systems which are stable systems, but also for unstable or oscillatory systems. Let's take a concrete example to see what this transformation does. Suppose we have a series circuit consisting of a resistance R of 50 ohms with a capacitance C of 227 picofarads. At a frequency of 7 megahertz, 40 meter band, then this impedance was equal to 50 minus J100 ohms. Let's now define a normalized impedance equal to Z over Z naught, as it showed up over here. Then Z over Z naught give us the normalized impedance 1.0 minus J 2.0, which will now map onto this unit circle. We can plot it on the Smith chart using the contours that are shown here. Each contour is labeled to allow you to pinpoint a point on the circle. So, for example, R norm equals 1.0. That's the real component of Z norm. That lies somewhere along this circle here. And you can see the value of 1.0. On the other hand, the imaginary component minus J 2.0 lies along a circle which comes up in this direction. So at this intersection is where the impedance 1.0 minus J 2.0 normalized lies. Whenever we have a point on the unit circle, in order to get it back to the impedances that we're used to dealing with, we have to multiply back again by the characteristic impedance. So 1 minus J2 on the Smith chart is equivalent to 50 times that, which is 50 minus J100. If we calculate the reflection coefficient gamma for this impedance, we see that gamma is equal to 0.5 minus J 0.5, or 0.707 square root of 2 over 2 at an angle of minus 45 degrees. Remember that gamma is a measure of how much voltage gets reflected back on a transmission line terminated in this impedance. And we'll see why the distance here, the length of gamma, becomes very important. Let's look at the location of a few important points on the Smith chart. If the load impedance is exactly equal to the characteristic impedance Z0, then gamma, which is Z load minus Z0 divided by Z load plus Z0 from the previous slide, gamma is precisely equal to 0. Well, that's a vector of zero length whose origin is the center, and that corresponds to the centermost point on the Smith chart. For an open circuit, you can see that gamma becomes plus 1, and that's a vector of unit length, which is at an angle of 0 degrees, and that corresponds to the rightmost point on the Smith chart. For a short circuit, gamma is equal to minus 1, which is, again, a vector of unit length, but its angle is 180 degrees. So the 3 points on the Smith chart for a short, open, and load are shown by those 3 points along the horizontal axis. It's also straightforward to show that all points which lie above the center horizontal axis have an inductive reactive component, and all points that lie below the horizontal center line have a capacitive reactive component. These 3 special points, short, open, and load, are those points that are used in the calibration of vector network analyzers. I have a presentation on the VNA which I gave to MARC a few years ago on my website at ak3y.com. One very important aspect of Smith's conformal mapping is that the voltage standing wave ratio is constant for any impedance which lies along a fixed circle around the origin. This can be seen from the relationship for VISWAR in terms of the reflection coefficient gamma. It can be shown that VISWAR is equal to 1 plus the absolute value of gamma divided by 1 minus the absolute value of gamma. So for a fixed length vector, in other words, for a fixed absolute gamma, the VISWAR is constant. Well, that's the definition of a circle. Notice that the closer to the origin one gets, the better the standing wave ratio. And of course, VISWAR equals 1.0 occurs exactly at the center where the load impedance is exactly equal to the characteristic impedance of the transmission line. Another very important feature of Smith's conformal mapping is that if I move a quarter wavelength down a piece of transmission line terminated in an impedance Z, then I rotate exactly 1/2 turn from where Z is located on the chart. So one full turn around the chart, which represents 1/2 wavelength, gets me right back to the same spot. And that's a consequence of that tangent term that we saw in an earlier equation. We'll find this result to be extremely useful in designing multiband J-pole antennas. Going back to our earlier example, if I attach a 1.4 plus foot length of LMR 400 coax cable to my load of a 50 ohm resistor and a 227 puff capacitor, that length, or roughly 17.4 inches, is a quarter wavelength at 144 megahertz. So the impedance rotates from the original point, which is 50 minus J100. It'll rotate 180 degrees around the Smith chart to a point diametrically opposite. And at that point, the normalized impedance is 0.2 plus J0.4, which corresponds to an impedance non-normalized, in other words, multiplying back out by the characteristic impedance of 50 ohms to be 10 plus J20 ohms. What I've done is I've taken this gamma term, which is a vector of a magnitude 0.707 at an angle of minus 45 degrees, and I've rotated it 180 degrees around, so that gives me a gamma of 0.707. Notice I haven't changed the amplitude at all, but just the angle. And I add 180 degrees to the angle, so it becomes minus 45 plus 180, which is 135, and it gives me a point on the Smith chart, which is located right here. So let's now use some of what we've learned to find the parameters of some transmission lines. In this example, we're going to be measuring the characteristic impedance Z0 and the velocity factor of a piece of twin lead. This will be the same twin lead that we'll be using later to build our J-pole antenna. Recall that from the previous equations, if a line is a quarter wavelength long, the source and load impedances are related via this relationship. And Z0 is equal to the square root of ZS times ZL, where ZS is the impedance looking into the line, ZL is the termination impedance of the line, and Z0 is the characteristic impedance. This relationship holds for a line which is exactly a quarter wavelength long. In this specific example, I cut a 21.5 centimeter piece of twin lead, terminated it in a carbon resistor of 1,000 ohms. I want to make sure that the load is purely resistive without any inductive or capacitive reactance that makes this equation a little bit easier to solve. And as we put this on the vector network analyzer and sweep the input of the transmission line from 1 to 500 megahertz, the vector network analyzer shows that we move along this trajectory, this blue line on the Smith chart. We start at a point which is close to 1,000 ohms, as expected. Near DC, the transmission line has very little effect. As we increase in frequency, you can see that the line becomes capacitive reactive up to a certain point, and it crosses the center line at a frequency of approximately 282 megahertz. At that frequency, we've moved a halfway or half turn around the Smith chart, which is equivalent to a quarter wavelength. So from the measured frequency that we see here, we know that a quarter wavelength with this dielectric material is 282 megahertz for a piece that's 21.5 centimeters long. But if we calculate the frequency in free space of a 21.5 centimeter line, it would show that it comes out to a frequency of 348.84 megahertz, much higher. The ratio of this measured frequency, which the line represents a quarter wavelength, and the frequency of the same section in free space is what's called the velocity factor. And the velocity factor is a measure of how much the wave front has slowed down due to the effects of the dielectric material. So the ratio of 282 megahertz measured in this quarter wavelength line to what the frequency would be in free space is 0.808 in this particular piece of twin lead, and that is the velocity factor. This velocity factor will be a very important parameter in designing our J-poles, as it takes into account the fact that electromagnetic waves are slowed down due to these dielectric effects, and it requires us to adjust dimensions in order to take this into account. Let's do another check on the velocity factor. In this example, I took an unterminated 40 centimeter length of twin lead. Again, we swept this from 1 to 500 megahertz using our nano VNA and got the blue trajectory shown at the left on a Smith chart. Again, a half turn on a Smith chart corresponds to a quarter wavelength distance along the transmission line. This is seen to occur when the frequency is equal to 149.3 megahertz, this point here on the far left. Note that we started at a infinite impedance, which is a point at the far right on the Smith chart, went a half turn around the Smith chart, and ended up at 149.3, crossing the center line. The free space quarter wavelength, however, would have actually been 300 divided by 4, which is quarter wavelength, times 0.4, which is the length of the piece of twin lead in meters, and that would have come out to be 187.5 megahertz. So the measured frequency of 149.3 is much, much lower, and this is due to the speed of propagation of the electromagnetic wave in that particular medium, which is a dielectric material. So the velocity factor is the ratio of those two numbers, 149.3 to 187.5, or 0.796, which is very, very close to what we saw before, 0.8. By the way, the manufacturer specified a velocity factor of 0.8, so while the characteristic impedance was 236 ohms instead of 300 ohms, the stated velocity factor by the manufacturer does look correct. Knowing this result, we can now determine the length we need to cut the twin lead to result in a quarter wavelength section at 146 megahertz, the center of the 2 meter band. In this case, the length is given by this equation. 300 divided by 4 is a quarter wavelength. 146 is the frequency in megahertz. VF is now the velocity factor of 0.8, and if I multiply these numbers out, I end up with a length of 0.41 meters, or a quarter wavelength is 16.18 inches in twin lead at 146 megahertz. But look at what else happens. If we continue to increase the frequency, we continue clockwise along the Smith chart. We see that the impedance continues to circle clockwise until it comes back to almost the exact same spot 1/2 wavelength later. In other words, an open quarter wave stub, which generates a short impedance, or a zero impedance, I should say, on the Smith chart, looks like a short not only on the fundamental, but also on all odd harmonics as well. So an open quarter wave stub for 2 meters will act like an open quarter wave stub on 70 centimeters. The fact that this rotation starts to move inwards with frequency, as we see here, the lines keep closer and closer to the origin, is a consequence of the losses that exist in the transmission line. The lossier the line, the faster the impedance trajectory spirals in towards the center. What this also says is if you have a very, very poor SWR at the terminals of your antenna, a very long, lossy coax run will mask that fact, making it look like your SWR is great, even though little to none of your power is actually making it to the antenna or is being radiated. Finally, another way to measure Z0, the characteristic impedance of a transmission line, is to use a formula given earlier, that Z0 is the square root of Z short times Z open, where Z short is the measured impedance looking into a shorted piece of line, while Z open is the measured impedance looking into an open section. Note that both Z short and Z open can be complex numbers, and of course usually are. In this example, I took a 39.5 centimeter length of RG316 coax, the material that we'll be using later in building the J-pole, and this will be the feed line that we'll use, as well as the quarter wave stub if we build a dual band version. At a frequency of 100 megahertz, Z short is given by 13.36 plus J 177.3 ohms, and that's measured on the vector network analyzer, nano-VNA. I can represent that as a magnitude in phase, and that's 178 roughly ohms at an angle of 85 degrees. I do the same thing for the open circuited piece of coax, and I end up with a impedance of 0.56 ohms with an imaginary part which is capacitive reactive with 13.73 ohms, and magnitude in phase gives me these numbers here, 13.7 at an angle minus 87. Note that both are complex, and they can be measured quite easily on the nano. So I take Z0 being equal to the square root of the product of those two numbers, and if I use magnitude and phase, it's much easier to compute the square root. These two equations come down to finally here, which gives me a impedance of 49.5 ohms roughly, with a small capacitive reactive component of 0.86 ohms. Note that in general, the characteristic impedance specified for a commercial cable is only an approximation, and you will often find this impedance is not purely real. Remember, our earlier results would show that for lossless cables, the characteristic impedance was real. However, for lossy cables, again, this is only an approximation. We also found in the Smith chart that a quarter wavelength occurred at a frequency of 130.2 megahertz for this piece of coax. So that's what we measured using the same techniques we did before. But the free space calculation would have given us 189.87. Again, 300 divided by 4, which is a quarter wavelength, divided by the length of the coax in meters, which is 0.395. That would have resulted in a free space frequency for quarter wavelength of 189.87. The ratio of those two, again, is called the velocity factor, and that's equal to 130.2 divided by 189.87, or 0.686. And in fact, the manufacturer states 0.69, so we're pretty much dead on to what the is called for this particular piece of coax. Again, these velocity factors are the important parameters, not so much the Z0. It's important for the cable that's driving the antenna to perhaps be 50 ohms, but in general, what's really important in designing the J-poles is to know what the velocity factor is for the various pieces of coaxes used. Let's leave for a moment our discussion of transmission lines and take a look at the half-wave dipole, an antenna that most of us are quite familiar with. Most of our experience with half-wave dipoles is operating them in a horizontal configuration. If we flip the antenna 90 degrees, as seen here, we have a vertical radiator which generates that familiar donut-shaped pattern as a function of azimuth and elevation. This pattern has a maximum intensity along the horizontal axis, which is ideal for terrestrial communications at VHF, UHF. In most cases, the dipole is typically fed from the center, where the driving point impedance is close to 73 ohms, making it a reasonably good match for a 50 ohm coax. However, in this vertical configuration, feeding the dipole from its center would produce a very awkward, if not impossible, mechanical situation. I have to somehow put the coax here, put it far enough away so it doesn't interfere with the dipole, and trying to mount this on a handheld would be a real bear. So in order to somehow keep the feed line from interfering with the antenna pattern, ideally you'd like to have the feed line perpendicular to the antenna, but this is not easily done for a handheld operation. So it would be nice to be able to, instead of feeding it from the center, feed it from the end. If we feed it from the end to feed the vertical dipole at the bottom, then we can attach that directly to our handheld radio. But what happens to the impedance, or the driving point impedance, when the feed is moved to that location? Hopefully this chart will shed some light on the dipole feed problem. Using EasyNet, I determined the driving point impedance for any point along the half-wave dipole. When D is equal to 0.5, it's in the center here, we are feeding the dipole where the impedance is modeled to be roughly 72, 73 ohms. In this case, 71.2 minus J3. As I mentioned in a previous slide, well, this is a great way to feed a horizontal dipole. Feeding one vertically is much more complex mechanically. As we move away from the center of the antenna, the impedance, both real and imaginary components, start to increase. So there's the real component increasing and the imaginary component increasing in a negative direction. When D is equal to 0.189, the magnitude of the impedance is roughly 200 ohms, and this feed point is used along with a 4-to-1 balun to drive what is commonly known as a Carolina Windom antenna. Moving further toward the end at positions between 0.1 and 125, the impedance varies from roughly 300 to 450 ohms, providing a decent match to twin lead, and this is sometimes called an off-center fed dipole. Finally, when we drive the antenna from its end, right here at the 0, we see that the impedance effectively skyrockets to values in the 2500 to 3500 ohm range. End-fed half-wave dipoles are another form of multiband antenna, which typically use 49-to-1 or 64-to-1 transformers to match the 50 ohm coax to these very high impedances. For our application, namely a vertically polarized half-wave radiator for handheld use, an end-fed configuration is ideal as we obviate the need for these really bizarre and special mechanical structures to attach the feed line to the radiator. However, we don't want to use a bulky transformer as used in end-fed half-wave horizontal antennas. So how do we transform this high impedance to something in the order of 50 ohms? Acts as an impedance transformer, transforming low impedances to high impedances and vice versa. As we saw, looking into the end of a half-wave dipole, the impedance is very large. In this case, we see that it's 1635 minus J2997 ohms, or roughly 3,500 ohms in magnitude, 70 times that of our 50 ohm coax. If we can add a quarter wave stub to the end of the dipole, then we should be able to transform it into a much more manageable impedance closer to that of our 50 ohm coax. And this is precisely how the J-pole works. In our case, we're making a flexible J-pole out of twin lead. A notch is cut in one side of the twin lead to create a quarter wave stub at the lower end. To the right of the notch in this diagram lies the half-wave radiator. Note that there's an effective parasitic element that is created by the notch. That's this element here. The element is not physically connected to the rest of the antenna, but rather acts as a parasitic element which tends to broaden the frequency response to the dipole. Remember that fat antennas typically have wider bandwidth properties. Looking into the radiator at this point, we see that the end-fed impedance is roughly 1600 minus J3000 ohms. Looking into that particular spot. This high impedance is then transformed by the quarter wave stub to a very low impedance. In this J-pole design, the quarter wave stub is actually shorted at its other end, right here. If we place the feed point somewhere along this quarter wave stub, then there is a point along the stub where we should be close to 50 ohms. High impedance on one hand, on the right-hand side, low impedance on the other side, somewhere in between. We've got to be able to find something which matches closely to our 50 ohm driving impedance. So how do we determine where to place that match for optimum SWR? From a circuit perspective, we can break the antenna into two parts. The top part consists of the half-wave radiator, that's this portion right here, plus the portion of the quarter wave stub that is above the feed point. So here's the feed point, and the portion of the quarter wave stub that's above the feed point is this portion right here. The sum of those two we'll call impedance Z1. The bottom part of the circuit consists of that portion of the shorted quarter wave stub that lies below the feed point. So below the feed point, we have a small section that is shorted on one end, and it's a piece of stub which is less than a quarter wavelength. We'll call that impedance Z2. So again, looking at the top figure, this is Z2, the portion below, and this is Z1, which is the portion above. The impedance that is seen by the feed line is simply Z1 in parallel with Z2. And that's shown by this diagram here. Now, it's a simple matter to determine these impedances and from them calculate the standing wave ratio as a function of tap position. But to do this, we need to make use of the Smith chart. As seen in this chart, the end of the dipole lies to the far right on the Smith chart. That's the point where we're driving at 1635 minus J 3000 ohms. This is where in this region where all the high impedances lie. The upper portion of the quarter wave stub starts to transform this impedance by moving clockwise along the chart. So we're moving this way along the chart as we increase the length of that portion of the stub here. In this case, after 14.7 inches, the transformed impedance is now 13.2 minus J 22.7, a tremendously improved impedance from where we started off at close to 3,500 ohms in magnitude. Looking at impedance Z2, which is the bottom portion here below the feed point, we start with a short circuit on one end. So we're starting at this point on the Smith chart. And again, we're moving clockwise along the Smith chart, an amount which corresponds to the distance of the tap point from the short circuit. So we move up the piece of twin lead, which is part of a stub, to the point where we reach the tap at this point here. So if we move 14.7 inches from the top down, and the entire radiating section is a total of 16.2 inches, the difference is 1.5 inches. So we move 1.5 inches from the bottom, and that moves that shorted section on the bottom of the stub to this impedance here, Z2, which is 0.12 plus J 43.8. So this is mostly an inductor at this point. Remember we said that if you have a piece of shorted transmission line that's less than a quarter wavelength, it acts as an inductor, and here's a good example of what happens. The feed impedance Z feed then is the parallel combination of Z1 and Z2. So we take those two impedances we just calculated, the one from the shorted stub up to the feed point, which is 0.12 plus J44, and the one from the antenna endpoint or end feed to the top of the stub where the coax is connected to our transmission line, and that's 13.2 minus J 22.7. We end up with an impedance of 40.8 minus J 21.4. From the Smith chart, this turns out to have a reflection coefficient of 0.25 at an angle of minus 100 degrees. So the feed impedance being the parallel combination of those then gives us a reflection coefficient of 0.25. Well, what's the standing wave ratio? The standing wave ratio then is equal to 1 plus the magnitude of the reflection coefficient divided by 1 minus the magnitude of the coefficient. So that's 1.25 divided by 0.75, or we end up with a standing wave ratio of 1.67 to 1. And so what we can do is we can do this for every single point along the bottom part of the curve of the stub. So we move it up 1.5 inches, 1.6 inches, 1.7 inches, et cetera, and calculate these two impedances, one from the top to the bottom and one from the bottom to the top, put them in parallel, look at the location of that particular point on the Smith chart in terms of its reflection coefficient gamma, and from gamma we can determine what the standing wave ratio is. So I went ahead and did this for our J-pole antenna design. In this slide I plotted the standing wave ratio for all tap positions from 0 to 4 inches from the bottom. As we can see, the standing wave ratio minimum occurs somewhere around 1.4 inches or so, and that corresponds to an SWR of roughly 1.7 to 1. What's nice is that the tap position for a good standing wave ratio, in other words less than 2 to 1 or so, is fairly broad. So this region here from about 1.2 inches to about 1.7 inches is where we can put the match so that we end up with a relatively good SWR. We don't have to be too concerned about how we tap that antenna in order to match the load. These drawings are taken from Dr. Edison Fong's articles on J-pole design that were published in QST magazine. The one on the left shows the single band J-pole design that we just described, while the one on the right shows a slightly more complicated dual band design. We know that a half-wave dipoles will in fact operate under third and higher odd harmonics. For the single band design, recall that the quarter wave stub per 2 meters at the bottom, it's this portion right here, will also act as if it's a quarter wave stub for the third harmonic, or 70 centimeters. Instead of a half-wave dipole at the top, though, if we operate this first antenna on the third harmonic, we now have a 3/2 wave radiator and not a half-wave radiator, and that occurs on 70 centimeters. Unfortunately, while the impedance match will be reasonably good, the antenna pattern on the third harmonic will not be, resulting in the radiating lobes aiming upwards and downwards instead of toward the horizon as with the fundamental frequency. This makes the single band J-pole operating on the third harmonic a very poor antenna, as it has significant null along the horizon, which is where we want to be pointing. And please take a look at Dr. Edison's articles for much more detail. In the dual band design on the right, we construct a half-wave antenna for 70 centimeters, and that's the 11.5-inch section right here. And again, drive it from the base. So we're driving it from the base of that antenna. And we're driving it with a 3/2 wave stub, which is equivalent to, 3/4 wave stub, which is equivalent to a quarter wave stub on 2 meters and a 3/4 wave stub on 70 centimeters. Remember that those have exactly the same properties of converting the high impedance of the end-fed 70 centimeter half wave, for example, in this case, to the low impedance driving source. But we still need to operate on 2 meters as well. So in order to do that, we can place an extremely high impedance at the top of the 70 centimeter antenna. So if I put a high impedance here, I can essentially choke off, at 70 centimeters that is, I can choke off what happens in this portion of the antenna for 70 centimeters. But if that high impedance can turn out to be a low impedance at 2 meters, then the rest of the antenna can be used to operate on 2. So by placing an extremely high impedance at the top of the 70 centimeter antenna, we isolate it from the rest of the antenna, and it has to be a low impedance at 2 meters, and this is simply done by adding a quarter wave stub for 70 centimeters at the top of the 70 centimeter half wave. That's this little portion right here. So at 70 centimeters, the stub looks like an open circuit. Remember, this is a short circuit on this end, and therefore, if it's a quarter wavelength long, it transforms the impedance from a short to an open. So at this point, at 70 centimeters, this little stub acts as if it's an infinite impedance. So when I operate this antenna on 432, the 432 energy doesn't see any of what happens above this particular stub because it's choked off by the high impedance. But if I operate on 2 meters, then this operates still as a quarter wave stub. This portion operates as part of the 2 meter antenna. The quarter wave stub for 70 doesn't look as like a stub anymore because it's no longer near quarter wavelength, so it acts as a piece of wire. And so the 2 meter portion of the antenna looks as if it's the composition of these 3 sections. It's a section below, which is the half wave dipole for 70 centimeters, the quarter wave stub for 70 centimeters, which was used to choke off the 70 centimeter antenna from the rest of it. And then the rest of the antenna is sufficiently long in order to let this entire length be a half wavelength on 2 meters. So since the 70 centimeter antenna now is a true half wave end-fed, it has an antenna pattern with a lobe that faces the horizon exactly as we wanted. And the same thing true for 2 meters. So this antenna works properly in terms of its radiation pattern for both 2 meters and 432. So let's summarize what we've learned. First of all, transmission lines can be mathematically modeled as distributed circuits consisting of resistive, inductive, conductive, and capacitive elements. This was done back in the mid-1800s by both Lord Kelvin and Oliver Heaviside to analyze the effects of wavefront propagation along transcontinental underwater cables. The resistance R and inductance L represent the properties of the inner conductor and shield, and the conductance G and capacitance C represent the properties of the dielectric material. We showed from the telegrapher equations that were developed by Heaviside that the steady state solution consisted of both a forward and reflected wave. The relationships between the reflected waves were shown by these equations here. Z0 is called the characteristic impedance of the transmission line. Gamma is a term which includes a attenuation constant alpha and a phase constant beta, and gamma is called the propagation constant. And for lossless lines, R is equal to G, which is approximately 0. And we can show that Z0, the characteristic impedance, is purely real with no attenuation. For lossless lines, we showed that the impedance ZS looking into a transmission line of length D and terminated in an impedance ZL is given by the relationship in the box above. ZS is equal to Z0 times the ratio of terms which involve the load impedance, the characteristic impedance, the length of the line, and the wavelength. Note that this function repeats every half wavelength, so the impedance is the same every half wavelength, and this is a consequence of the tangent function. We looked at 4 special cases, one where the transmission line is terminated in its characteristic impedance Z0. In this case, we showed that ZS, the impedance looking into the line, is equal to Z0 no matter where you are along the line. This is the case of what's called a matched transmission line. In the case where the line is left open on one end and the length is less than a quarter wavelength, the line acts as if it was a capacitor. Similarly, if the line is shorted and the length is less than a quarter wavelength, the line acts as an inductor. And those two concepts become very useful for microwave, microstrip, and designs where you have a very difficult time building a physical capacitor or inductor. Finally, the most important one for our J-pole design and analysis is the case when the length of the transmission line is precisely equal to a quarter wavelength. In this case, we see that the transmission line acts as an impedance transformer. High impedance loads get transformed into low impedance sources. Low impedance loads get transformed into high impedance sources. And this will be very useful, as we saw in designing the J-pole to operate on multiple bands. As far as the J-pole is concerned, the J-pole is essentially a vertical half-wave dipole, which is end-fed from the bottom. This eliminates the problem associated with the support structure for center feed, making it usable for handheld radio applications. However, as a driving point impedance of an end-fed dipole is extremely large, on the order of 3,500, 4,000 ohms or so, some mechanism is needed to transform to a 50 ohm feed from this high impedance. And as we saw, and had several examples to illustrate how that behaves, we saw that a quarter wave stub is a perfect impedance transformer. So the J-pole uses a tapped, shorted quarter wave stub to transform the 50 ohm coax to the high impedance needed to drive the end-fed dipole. There are really only 3 design parameters for a single band J-pole. One is the length of the half-wave radiating element. One is the length of the quarter wave stub, which drives the radiating element. And finally, the tap point on the quarter wave stub to obtain the lowest standing wave ratio. We have shown how to use the nano-VNA to determine characteristic impedance and, most importantly, the velocity factors for a given piece of coax. From these measurements, we could determine the lengths for both the radiating element and the quarter wave stub. The nano-VNA can be used particularly to optimize the design by monitoring standing wave ratio by trimming both the stub and radiating elements. And finally, multi-band J-poles are a straightforward extension of this single-band concept. An additional quarter wave stub is used to isolate the high-frequency mode from the rest of the antenna. Thank you very much for listening to this presentation. If you have any questions, please feel free to contact me at ak3y@arrl.net. Thank you very much.